Right. Let's get started. So, application task 2 is out. Just like application task 1, I don't have the grader out yet, but I'll get it either tonight or probably tomorrow morning at the latest. Last time for AO1, I got it out at like 2 a.m. on Monday night, technically Tuesday morning. So it might be late at night, but I plan to get it out tonight. Grader's almost ready. I just got to touch it up. But I didn't quite get there last night or this morning. So for this one, what do we want to do? This is going to be a calculator. We're going to implement a calculator. And you have a decent amount of starter code here, though a lot of it, don't get intimidated by the number of classes here. Most of these do very little. All they're doing is routing method calls from the front end to the back end. And if you take this class, there's a decent amount of code in this class here, but it's one of them cases where you don't have to understand anything at all of what's going in here. You don't have to modify this class. You don't have to think about it at all, but you can run it. So if we run this class, calculator GUI, graphical user interface, we'll get a calculator, which does absolutely nothing. But this is what we want to build, is a 4-function calculator. We can add, subtract, multiply, divide, and we want to implement this to do things. This GUI, whenever a button is pressed, it's going to call methods in this calculator model class, or calculator.model.calculator. And this class has a method call for each one of the button presses, with kind of the exception of number press takes a number. So we have one method for 10 different buttons for the number buttons. And we have a method for every single button, and one method display number, which will return the number that should be displayed on the screen of the calculator. And this is the only code that you'll implement. If you want to ignore everything in the controller package and everything in the view package, that's perfectly fine. The only code that you're modifying is in the model package. So your goal is to implement the calculator class to actually do calculator things. And by that we mean when the sequence of buttons are pressed, check what number is displayed to make sure it's displaying the correct number. For this, you have full freedom in the model package. You can create extra classes, you can create sub-packages, you can create more methods. You can do whatever you want here. But in your tests and in my test, we're only going to use anything that was given in the starter code. We're only going to call these methods. But these methods can create classes, modify state. You can do anything you want in these methods. But in your test, only call these methods. Those are the only methods the GUI is going to call. Those are the only methods we're going to call in the testing. So that's our goal, is to implement this calculator in the model package. With full control, you have full freedom of what to do in the model package. But you can't use control flow. So we talked about this last week, but just to formally introduce it, you can't use any control flow. This includes conditionals and loops, any type of conditional, if, else. Our switch case statements, which I don't think ever came up this semester, but it's a way, if you have like if, else if, it's a way you could clean that up if all those conditions rely on the same value. And we did talk about throw, try, and catch. There's also finally, which is part of that family. These are banned too because they can be used to simulate conditionals, and really throwing and catching exceptions is a way to control the flow of your program. They do very similar things to conditionals, just in a different way. Loops, unfortunately, these have to be banned because they can be used to simulate conditionals as well. If you have a while loop with a conditional, and then at the end of the while loop, switch that, make some change to make sure that that conditional is going to be true, then it's effectively an if statement. Same thing with a for loop, same thing with do while. And also any way of breaking the assignment in a way that is against the spirit of what we're doing here. If you find a way to simulate, and there are other ways, to simulate conditionals without using any of these banned keywords, then it's a no-go as well. As long as I'll do a pass to look for that kind of stuff. If I find you doing that, going to remove your credit and could potentially, I don't think I would, but could potentially go an AI route on that. Depends how egregious it is. If it's really blatant. But I probably wouldn't go that way. But I could very well take away credit on the assignment if you violate it. So if you're, the general rule of thumb here, yeah, I wouldn't go AI on that. That'd be a little cruel. But the general rule of thumb, if you have code that you wrote that's being ran conditionally, that's against the spirit of the assignment. So if you have some logic that's going to say either run this code or this code, depending on the value of something, that's going to be against the rules, which is what a conditional is. If some Boolean expression, run this code, else run this code. If you simulate that in any way, that's just, it's defeating the purpose of the assignment. You're not learning what you're supposed to be learning from the assignment if you do that. And this includes your tests. So the first thing Autolab will do is look at all of the files in your submission and look for any of these keywords. Any of these keywords show up in your submission at all, it's going to reject your submission. It's not going to compile, and you'll get errors in Autolab. So that does include your tests. Some clever students like to hide conditional code in their test package. So unfortunately, I do have to ban it in the test package as well. So that's that's not the assignment. I haven't talked about the whole thing yet. So that's what our restriction is. And just to get this preface out there right away, this disclaimer, I'll probably say this a few times throughout the week. By no means at all am I saying conditionals are a bad thing. I'm not saying loops are a bad thing. I'm not saying any of this is a bad thing. But what we want to learn about, what this week is all about, is the state pattern. And by banning these things, this is my artificial way of forcing you to get practice with the state pattern. So to complete this assignment, the answer is going to be the state pattern. So if you're thinking, how am I ever going to do this without any conditionals or loops or anything? The answer is going to be the state pattern. I'll show you all week how to do that. But if I allow you to use conditionals, because I've done that before, I'm like, here's what the state pattern, I spent a whole week in lecture explaining the state pattern, and then I give the assignment, I say, use the state pattern to do this, and everybody in the class uses conditionals and doesn't use the state pattern at all. So I found it effective if I just ban these. You actually have to use the state pattern, because I want you to get practice with the thing that we're teaching. So I think it's a cool thing. It's a useful exercise. But outside of this assignment, by all means, use all this stuff. This stuff is great. It's fundamental programming tools that you should be using all the time. So clone the repo. That'll give you the code that we just saw. And the application objectives are broken down into two things. I'm not gonna go through all these and break them down, but it's generally what a calculator should do. The way I designed this, I open up my calculator on my laptop. I just kept hitting buttons and playing around with all the functionality until and then coded up, wrote up how all that works, and then coded it in my solution. So it's what you would expect from a calculator, but importantly, we have a list of undefined behavior. So these are things where the situation, sequence of button presses that were not going to define what should happen when these buttons are pressed in this order. We're just not going to define it. And in general, anything that's not explicitly defined above in this document is undefined behavior. I think I have a comprehensive list of explicitly saying what that undefined behavior is. But if I'm missing anything, let me know. I'll add it to this list and make sure we're all on the same page of what's undefined behavior. So any of this undefined behavior, I'm not going to test it. You're not going to test it, because we don't know what the expected output should be, so let's just not test it. And this is an attempt to reduce the complexity of the assignment. This assignment can get out of hand, and I've ran a version of this assignment before where there was no undefined behavior. Students had to implement everything was defined. I had several pages of this is what should happen in this situation, this is what it should do here, this is what should be displayed at all times in different situations. It gets complex pretty quick. But that version was a 3-week assignment, and this is a 1-week assignment. So we're going to have undefined behavior and just avoid these situations. Your code, whatever you do when these situations occur, it doesn't matter what your code does, because I'm not testing it, you're not testing it. Let's just avoid it and let this assignment not get out of hand. Any questions on that? Or any questions besides, how the hell are we going to do that without conditionals and loops? And luckily, the testing, the no conditionals or loops in testing, that restriction shouldn't even hurt that much. Just the way that the calculator kind of begs to be tested doesn't really lend itself well to having a data structure of test cases and then looping over those test cases. Just doesn't really lend itself well to that anyway. Writing my tests, I never missed conditionals or loops in my test cases themselves. So I don't think that's going to be too big of a restriction. In the code, you're going to miss them. You're going to miss conditionals. So how are we going to do that? How are we going to do that without any conditionals? And the answer is the state pattern that we're going to spend all week talking about. So the state pattern is a design pattern. We incidentally just happened to come across one other design pattern last week. We came across the factory pattern. It came and went, super brief, but the library we were using for the Twitter API happened to use the factory pattern, and we talked about it briefly. So that's an example of a design pattern. This week we're going to talk about the state pattern. We're going to spend a whole week. This one will not come and go real quick. And this one we actually have an assignment on and everything. So this is called the design pattern, which is a solutions to common problems that we face in object-oriented programming. If you're interested in these things, which they can be interesting, there's a whole bunch of patterns, and I believe we've actually used a few of them this semester. I just never called them by name because I just think it's kind of natural to use them. I don't think of them as like a separate thing. I just think of it as part of OOP. But I think we used a couple of them. But your search term is Gang of Four if you want to read up on these things. There's a whole bunch of them, and they can be useful in different situations. The Gang of Four, these are four, I believe they were all consultants, and they got together over a long weekend, I believe. They wrote these things up pretty quick. But they all consulted for a lot of different companies, a lot of different software shops, and saw a lot of common problems and the developers' solutions to those problems, and noticed certain patterns that a lot of problems came up across a lot of different companies and teams, and they had similar solutions to those. So they decided to just kind of codify that up and write up, here are a bunch of common things that we see, and here's how you can solve them. And they called them design patterns, and they published them and said, here's some stuff that'll help you out. So then we don't have to resolve these problems every time. We can just use those existing solutions that are out there. So the state pattern is a good application of polymorphism. If you're still fuzzy on polymorphism, this one's going to be tough to understand. But if you're good on polymorphism, here's a cool way that we can use it to change how our code works. So every object has state and behavior. This is something we've been talking about since week 3 when we first introduced classes and objects. Every object has state and behavior. And the behavior can depend on the state of the object. So the behavior can ask its state, what are the values of these instance variables, and then change its behavior based on that state. Right? But what if we want to significantly change the behavior of an object? So what if an object really changes its behavior based on its current state? So, for example, what if we had a class for H2O, and we want to say if this dot temperature greater than 212 Fahrenheit or 100 Celsius, whatever our units are, we want to say if the temperature is beyond some threshold, then we're going to have some certain behavior. If it's not beyond that threshold, we're going to have very different behavior, whether we're a gas, liquid, or solid. We're going to have very different behavior in our different states of the same object. It's the same substance, it's the same thing, but it's going to have different properties and different behavior depending on its current state. So we're just going to use if statements, right? This is what we would naturally do. And in most cases, this is going to be the right answer, by the way. The state pattern is not the answer for everything. Most cases, you'll just want to slap a conditional in there and be done with it. So we have some conditional. We'll say if temperature, do this, else do this, maybe an else if in there. And this is fine. But what if we want to expand this functionality? What if it's not H2O that is going to have 3 different states? What if we have an object that should have a lot of different behavior? I said states. I'm getting ahead of things. That has a lot of different behavior depending on certain conditions. We're going to end up with code that looks like this if, else if, else if, else if, else if, else. We're going to end up with code like this. And even then, this sometimes isn't the worst thing, but it gets really bad when this behavior is very different for each conditional, and when that behavior might be 10, 20 lines each, and we have a 100-line if statement with if, else if, else if, else if, else, spanning 100 lines. Now it starts to become a problem. It starts to become cumbersome. It's hard to work with this, which means it's going to be hard to read. Which means you're working on a team, you got code that looks like this in 100 lines or even more of a file, and you got the new hire, and your job is to get them onboarded. You're spinning them up and getting them used to the project, and you say, okay, let's go through this method, let's talk about how this project works and everything. And they have to read this huge if block with all kinds of different behavior, keeping track of which else if block they're in at any time. It gets painful. At some time throughout your career, you're going to come across something like this, and you're going to hate it. Code, even if it's not this specifically, you're going to come across code that's completely illegible, and it's painful. So hard to read, which means it's hard to onboard new developers, which means you're the one who has to maintain that code all the time. And it is going to be hard to maintain. Customer comes along and says, I want another feature. I want the code to do this also. And you have to add another else if somewhere in this code. That's going to get hard to do as this gets more and more complex. So if you want an else if, maybe it makes sense to add it right here. Now you have to make sure you're checking all of the interactions between the conditionals, because you're assuming that these 3 are false if you have your behavior right in between 2 and 3 here. And you have to make sure the first 3 are false every single time you want that 4th one to be the behavior that you have, among other things that make this hard. Of course, it gets harder to read. You're adding another 20 lines maybe. It gets very tough to maintain, tough to add new behavior. And when you do add that behavior, retesting everything, making sure you didn't break anything else, because it'd be really easy to break. Looking on the other side, if you add an else if right here, and sometimes when that conditional is true, you might have wanted behavior 3 or completely different behavior. But now if you have that conditional, which happens to be true in some of those situations, you have to test for that and make sure that's not happening. And that test is going to be really complex because you have to hit every different combination of these Boolean expressions being true and false. You got to hit your whole truth table on that one, and that can get cumbersome. So tough code to maintain, tough to expand, and that's our goal for a lot of this OOP discussion. Before it was adding new game items to our game, we want to make sure that's nice and easy. We just create a new class and slam that game item in our game. We want it that simple. When we have something like this, it's not that simple. It's not that easy to expand this code where we have one chunk of code that's doing a lot of different things. We can't really maintain that very easily. Start going to your customers a lot and saying, well, it would take us a month to add that feature. I'm sorry, we can't. No, we want to go back to our users and say, yep, yeah, we can do that. We can add that. Here, we'll whip up a prototype in an hour. Do you like this? You can beta test it. You like it? All right, we're going to put that in the next release. That's what we want to do. Okay, so let's try the state pattern. So that's the problem. Now let's solve it. Let's use the state pattern, where instead of changing behavior based on the value stored in certain variables, which is what we do with conditionals. We say if the value in this variable meets some condition, then do this, else do this, else if, whatever. We're checking based on the value stored in a variable, Instead, we want to change behavior based on the type stored in a variable. This is the big change that we're going to do, and that's the core of the state pattern right here, is we're changing behavior based on type, not value. So our object that has all the different behavior is going to not define any of that behavior. When we have our object, it can have a multitude of different behaviors. We're not coding that behavior in that class. The class is going to end up not really doing anything. Instead, it's going to have a state variable. It's going to have an instance variable which stores an object representing its current state. And that state is going to control what the object actually does. So when the object gets a method call, it's not going to handle that method call itself. It's going to go to its state and say, hey, state, this method was called, do your thing. And then the state decides what should be done. And it's going to do something different depending on the type of that object. So each one of your different states you can be in are all going to implement, here's where polymorphism comes into play, are going to implement an interface or extend an abstract class or extend a concrete class, however you want to set it up. It's up to you how to do it for the homework. It'll be an interface in the example I'll show. Are going to implement a common interface. The variable of the object that's going to have different behavior will have a variable of the type of the interface, and then depending on what type the object is that's currently being stored in the interval, that's what's going to change the behavior of those method calls. And when we do this, what we're going to see, we're going to have a trade-off. We're going to have a lot more classes, a lot more methods, a lot more stuff to define, which can get harder to wrap your head around. Talking about a new person coming onto the team, they're going to see a lot more classes, and they're going to have to flip around a lot more files to figure out what something does. Can be a little bit harder to read, or a little bit harder to wrap their head around the architecture, but each method is going to be much simpler. Every single method call, every single piece of functionality is going to be very, very simple. So a single method call will be trivial to understand, but sometimes getting the big picture will be a little tougher to understand. So it's a definite trade-off. The state pattern is not the answer for everything. For each situation that you run into, you have to decide for yourself, is the trade-off of the state pattern worth it? It's definitely not a you'll use this all the time thing. It's if you have a specific situation where the state pattern makes sense, then use it. It's probably the first thing we're learning about where it's not like, this is just fundamental, you use this all the time. If you have to open a file, here's how you open files, and you're going to have to open files. State pattern is, you really have to decide, is this right for my problem? Is this right for the architecture that I have? So our state is either an abstract class or an interface. It'll be an interface in the example, but very well can be an abstract class if you want a constructor, if you want instance variables, if you want default behavior of your methods. It can very well be an abstract class. And this is what's going to define the API. These are all the methods that the object is going to defer to its state for functionality, for behavior. Each concrete state that implements the interface or extends the abstract class is going to implement all of the methods for the API and define what should happen when the object is in that state. And each one of those states is going to have a reference to the object to which it's attached. We'll see that throughout. So it can have access to all the instance variables and be able to modify those instance variables through various getters and setters. We want to be able to have the state be able to change the instance variables of the object to which it's attached, which will include the state itself. Okay. All right, that's a lot. So so that's everything. That's the state pattern, all in theory, all in text and everything. Let's actually hammer that down with an example, though. I don't expect the state pattern to make sense through what I just said, but I wanted to get all the theory out there. This is what the state pattern is. And now let's make it make sense through an example. So this is Bruce Banner. I assume most or all of you actually know who Bruce Banner is. If not, maybe a few of you who don't, fictitious character who's a world-class scientist. He can drive a car, for what it's worth. We'll see why that's important in a minute. And he's not very good in a fight. If Bruce Banner's with you and you're ready and you got a fight coming, he's just not gonna help you out. But make Bruce angry, and he becomes the Hulk. The Hulk has very different behavior than Bruce. The Hulk is great in a fight. He's really going to help out. He smashes cars. He can't drive them. And he's just completely out of control. One man, two very different behaviors depending on his current state. So let's code this up. We want to take this idea, take this concept, and code it, simulate this in code, and get the differences between these two states using the state pattern, of course, to change the behavior of Bruce Banner depending on what state he's in. And I'll name these states Dr. Banner and the Hulk. So Bruce Banner can be either Dr. Banner or the Hulk at any given time. And of course, we won't use conditionals during the code. So let's implement the Bruce Banner class first. Let's start there. The Bruce Banner class is going to have these four methods, just the methods that we're going to add to our API. The methods that can be called: make angry, calm down, use cart, and fight. And instead of actually implementing these methods, when we're using the state pattern, we're not going to implement functionality in this class unless the functionality is the same regardless of state, which happens sometimes. Maybe the clear button on your calculator always does the same thing, for example. Hint. But we're not going to implement any of these methods. Instead, we're going to have a variable that controls the state of Bruce Banner. And for these methods, we're going to defer to the state. We're going to say, hey, state, the make angry method was called do your thing. And depending on the type stored in that variable, we're going to get very different behavior due to polymorphism magic. So we're going to have the state interface, which defines those four methods that can be called. Our variable is going to be of type state. And then in our two different concrete states that we can be in, Dr. Banner or the Hulk, we're going to implement the state interface. We're going to have actually I want to talk about that in a second. And we're going to implement all those methods to say, this is what should happen when these methods are called while we're in this state. So Bruce Banner is initially in the Dr. Banner state, and each constructor of these states is going to take a reference to the object to which it's attached so we can access the state and behavior of that object. So we're going to pass an instance to Banner. We're going to have an instance variable of Banner, store it in the instance variable. This is all boilerplate, but all this to say that we need an instance, we need a reference to the object to which that state is attached, or the object that state's controlling the behavior of. So we want a reference to that object. And we're going to pass that object in the constructor. So this line of code is executed while the constructor is being executed. And when a constructor is running, this is a reference to the object that's being created. So we're going to pass a reference to the Bruce Banner object that's being created to the state. And we're going to set the initial state to Dr. Banner. So when we first create a Bruce Banner, or when Bruce Banner's born, he's going to be born as a doctor, I guess. And we're going to pass a reference to Bruce Banner to that Dr. Banner state. Now when a method is called, say we call the Bruce Banner's fight method. Bruce Banner says, I don't control my own behavior. Hold on, let me defer to my state. This .state, which is an object, reference to an object of type Dr. Banner, .fight. So we go to the Dr. Banner class to decide what is going to happen. We go to its fight method and call this method when fight is called. If we were in the Hulk state, if state had a reference of type the Hulk, and we call fight, this .state.fight would go to the Hulk class if the object is of type Hulk, and call this method instead. So the behavior of the Bruce Banner object depends on the type of the variable referred to by its state variable. So we're changing behavior depending on the type of that variable. I got ahead of my slide here. I already said all this stuff, but I'll let you look at this for a second while it sinks in. No, I guess I have this to say. So when we're coding the Bruce Banner class, nothing in the Bruce Banner class except the initial state, nothing in here cares what type this variable is. Nothing cares what state it's in. We're not hard coding anything. We're not saying if we're in the Hulk state, do this, else do this, or whatever. Not doing anything like that. Nothing about this cares what state we're in. We're just going to defer to the state, and whatever state we happen to be in, that's going to control what behavior we get for those method calls. And the one thing that I purposely skipped over are these two lines right here. So let's talk about these two. This is the last piece to our puzzle here to understanding the state pattern. This is a state transition. So we're initially in the Dr. Banner state. So how do we ever get into the Hulk state? We're going to hit a state transition, and this is why each state needs a reference to the object to which it's attached. It's so it can access and change its instance variables, including the state itself. So when Bruce Banner's in the Dr. Banner state and make angry is called, Bruce Banner's going to defer to the Dr. Banner state and say, hey, state, what happens when make angry is called? The state's going to say, well, let's see, I'm of type Dr. Banner, so let me go to the Dr. Banner class and look that up. It's going to be the make angry method here, which is going to say, and there's no this right here, which bugs me a little bit. I thought I got them all. Oh, I missed it right here, too. Both state transitions. I got one of the four in the state transitions. Anyway, so we're going to go this dot banner. So we're going to the reference of the object, the Bruce Banner object that we're attached to. We're going to call it set state method and set its state to a new instance of the Hulk state and make sure that we forward that reference to the Banner object, the Bruce Banner object that we're storing, to tell the new state the object to which it's attached. So after this, after make angry is called, when we're in the Dr. Banner state, we're going to transition to the Hulk state by replacing the variable controlling the state, replacing that with an instance of the Hulk. And the Hulk and Dr. Banner both implement state. That variable is of type state. So it's a valid assignment through polymorphism. But now, when another method is called, after we transition to the Hulk state, now we get this set of behavior. We completely change the behavior of Bruce Banner by calling one method that had a state transition in it. And then in the Hulk class, say we call make angry again, we have the same method called twice in a row, but the second time we're going to get very different behavior than we did the first time. The first time triggered a state transition, and the second time is going to call the Hulk method for this. And then finally, if we're in the Hulk state and we call calm down, the Hulk state is going to go to that Banner object and change its state back to an instance of Dr. Banner, which swaps all of this functionality out for this functionality again, and this is our behavior back in the Dr. Banner class. And as a side note, there's some of you who might be bothered by this. I'm a little bothered by this too, but not too much. That every time we have a state transition, we are creating a new object for that state, which isn't super memory efficient. If we have a lot of state transitions, we're going to create a lot of objects that are going to get garbage collected and then create new objects that are effectively the same thing. So one way we could get around this is create singletons for these, which incidentally is another design pattern. Another design pattern where we have one object of each of these types, and then we reuse that same object instead of creating new ones over and over again. We could do that. I'm not going to bother for 1.16, but that's something you might want to do. If you're releasing this code for production use, you would probably use singletons here. Might be a case where you'd want to use singletons. It's pretty rare when you want to use a singleton, but this might be one of those opportunities. Actually, maybe not. Maybe I wouldn't. But we don't need to go too far down that sidetrack. If you use singletons, you can't create two Bruce Banner objects, which in this case is probably a good thing. We don't want two Bruce Banners hanging around. Of course, with time travel and multiverses, maybe we do, so that would lock us down. But anyway, that's not what we're here to talk about. So that's the state pattern. So any questions on this? Here's the whole code, with the exception of the car class. If you go to the repo, there's a car class. It doesn't really do much. The Boolean here, car.drive, and then I have a magic Boolean here. This is whether you're going to damage the suspension or not. Dr. Banner's not going to damage the suspension. He just drives the car just fine. The Hulk is just going to destroy it. So any questions on this setup, this pattern? We have changing behavior, no conditionals. Bless you. No questions? I'll move on. Okay, so this is all well and good, right? Well, no. I think it would be very fair if you made this argument. If you said, "Why the hell would I do that? Why wouldn't I just have a Boolean that says is Hulk as an instance variable, and then in each one of those four methods, I'm going to say if is Hulk, do this, else do that." It uses conditionals. It's more complexity in each one of those methods. But I don't have to have three classes in an interface, and I don't have to understand the state pattern. I don't have to do any of that. I'm just going to slap one Boolean and a conditional in each one of those methods. And I think you'd be right. I think this is a case where that would be perfectly fine. It wouldn't clutter up the code that much. It's not that bad. Where we really get the power of the state pattern is when there's more states. So meet Professor Hulk. This is a third state that Bruce Banner can be in. This is when he's in his Hulk form, but he has full control. He has all of the scientific knowledge and ability as Dr. Banner, but he's great in a fight and has all the advantages of the Hulk, but without going crazy and not going out of control. This is a third state he can be in. Very different behavior from either of the other two. So how do we add this to our code? Well, if we're using a conditional, if we're saying if Boolean is Hulk, initializing that to false, and then switching state based on that Boolean, we have a little work to do if we want to change that. We have a few options. We could change the state to a string and have that string be the Hulk, Dr. Banner, or Professor Hulk. And then in our four methods, we'll say if that string is the Hulk, do this, else if it's Dr. Banner, do this, else if Professor Hulk, do this, else invalid state, everything breaks. One typo in a state transition, you'll have invalid states and things like that. You could do two Booleans. You could say is Hulk and is Professor Hulk. And then if is Hulk and is Professor Hulk, then do the Professor Hulk stuff. Else if is the Hulk and not Professor Hulk. Like you can do that too. But any of those solutions, any solution is going to be a little messy. We're going to start seeing how it gets messy. Even just with 3 different sets of behavior, it's going to start being difficult to manage, difficult to maintain, difficult to add features to our code. You're going to start getting really messy code. With the state pattern, no big deal. We're going to create the Professor Hulk state that implements the state interface. We have our boilerplate to get the reference to Bruce Banner, and we write each of our 4 methods. Now, when you're embracing the state pattern, when you're writing one of your states, it should be very easy to write your code. It should be very easy because you're very narrowly focused. You're not thinking, okay, I have this big old conditional, so if I make it into this portion of the conditional, that must mean that I'm in the Professor Hulk state. We don't have much to think about here. We don't think about it like that. We say, I'm in the Professor Hulk state, and make angry was called. What should happen? It's a very specific thing. Very easy to write this method. If I'm Professor Hulk and make angry was called, what happens? Well, nothing. What happens when calm down is called? Well, nothing. What happens when I use a car? He's going to drive the car, but he's probably going to damage the suspension. He's a big old boy. And a fight, he's going to do pretty good in a fight without going out of control. It should be very easy to write your methods once you have your states. The challenge for the homework is going to be determining what states you should have and what the behavior should be in each of those states. But once you have everything planned out, actually writing the code when you're using the state pattern should be the easiest part of developing software. So it's very much a design problem as opposed to a coding problem. And then we're going to add our state transitions. I am cheating a little bit here for the slides. I'm going to put learn control in the Bruce Banner class. This is what we'll do whenever we have behavior that we want to be the same regardless of state. So whenever Bruce Banner learns control, whether he's the Hulk or Dr. Banner, I don't care. If he learns control, he's going to transition into the Professor Hulk state. So since I cheated a little bit, we didn't have to change the Dr. Banner or the Hulk states at all. And if we did change them, all we would be doing is adding in our state transitions. How can we enter the Professor Hulk state? That's all we're asking. At what situations, which method calls and which states would we transition into the Professor Hulk state? That's the only thing we would ever change. And I put that all in the Bruce Banner class. So it's that easy to add a state. And whether you're adding your 3rd state or your 100th state, it's still just as easy. You implement that state, add in your state transitions of how you get into that state, add your state transitions of how you get out of that state and which states you go to when you get out of it. For Professor Hulk, we're going to say there's no escaping. Once you're in Professor Hulk, you're done. You're in there forever. So we don't have any state transitions going out. But if we did, we would just add a state transition in the same style that we had before. I got ahead of my slides again. So very easy to add a new state. We had that 3rd state. We're using most of the code that we had. But if we're going into these methods, if these methods are if is the Hulk, do this, else do that, we have to go into that conditional and make fundamental changes to our code, which means we're going to want to retest that, and it's somewhat likely that those tests are going to fail the first time. We're probably going to break the code the first time we change that, and then go and say, oh, we had a typo here, whoops, then fix the typo. But you're going to have to retest all that code because you're going to have to change everything. All of what you've done has to change. You have to completely restructure your entire class to add that 3rd state. With the state pattern, none of that. State transition and add the 3rd state. With a state pattern, it's helpful to draw our state diagrams. And this is something I like to ask in office hours. You're sitting there in office hours working on the calculator, and you're like, man, I just have no clue. I like to say, show me your state diagram. And you'll say, I don't have one. And then I'll say, let's write one together. And then we'll have fun writing a state diagram. So a state diagram is going to be each of the states that you can be in, that your object can be in, and any of the state transitions. What method calls are going to trigger state transitions? So with Bruce Banner, his initial state is Dr. Banner. If you call make angry, he's going to transition to the Hulk state, and he's going to get all of the Hulk behavior. Call calm down, he's going to go back to the Dr. Banner state, and whether he's Dr. Banner or the Hulk, if he learns control, he's going to transition to Professor Hulk. And once he's in Professor Hulk, there's no arrows going out. He can't transition back to one of the other two states. In our simulation, anyway. So, when using the state pattern, say you're in a situation where you have to use the state pattern, like when you're coding application task 2. What do you do? So here's my recommended flow for doing that. Start by writing your API. For the homework, this one's trivial. It's already in the handout code. You already have the API. Even if I didn't give it to you in the handout code, I gave it to you in the handout code just to reduce like typos. If you call it number pressed with a lowercase p by accident, I'm trying to limit those things. But if I didn't give it to you, the API matches the buttons on the calculator. So when you have a physical device, the API is easy. It's the buttons that the user can press, all the actual physical inputs the user can put, plus the number that's displayed on the screen. That's your only output, and that's the only thing you call in your test to make sure everything's working the right way, is that display number method. So your API is already done for you. The next two steps are a bit trickier. Decide what states should exist and the transitions between the states. For this, what I recommend doing is think through what your calculator should do, go through the document, all the features that should exist, and ignore all the undefined behavior too. But go to your calculator and think, what should each button do when I first start up the calculator? So you'll be in whatever your initial state is. You can call it whatever you want, but whatever your initial state is when you first fire up the calculator, each button is going to have a certain behavior when you press it. And then sometimes when you press certain buttons, the behavior of other buttons are going to change. So if you ever have a button press where you're like, okay, if then I press plus, if any button on the entire calculator changes what it does after you hit that button, that's a state transition. You have yourself a new state. And keep going through, simulating buttons, thinking it through, and drawing your state diagram as you're going. And think of what button